Hai Agus.
Saya mulai ya, Mbak Cica. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore Bapak, Ibu, dan rekan-rekan sekalian. Selamat datang dan terima kasih atas kehadirannya pada Kolokium Fisika Kuantum Badan Riset dan Inovasi Nasional BRIN. Kami juga mengucapkan selamat menunaikan ibadah puasa bagi yang menjalankan. Semoga kita tetap diberi kesehatan dan kekuatan dalam menjalani ibadah dan ibadah kita diterima oleh Allah Subhanahu wa taala. Amin. Bapak Ibu sekalian, sebagai informasi bahwa Kolokium Fisika Kuantum BRIN ini rutin diselenggarakan setiap 2 pekan sekali, biasanya pada pukul 13.30 sampai dengan 15 waktu Indonesia Barat, dengan menghadirkan pembicara dari internal Pusat Riset Fisika Kuantum BRIN maupun pembicara tamu dari luar BRIN. Untuk hari ini, Kolokium diselenggarakan pada jam yang tidak biasanya ya, rekan-rekan semuanya, karena memang menyesuaikan dengan waktu pembicara yang saat ini berada di luar negeri. Nah, Kolokium Fisika Kuantum ini menyajikan berbagai macam topik ya yang sangat beragam, dari fisika partikel hingga fisika material, dan insya Allah kita akan rutin menyelenggarakan Kolokium ini hingga setidaknya pada akhir tahun 2023. Nah, untuk hari ini kita menghadirkan pembicara dari eksternal Pusat Riset Fisika Kuantum BRIN ya. Beliau merupakan Postdoctoral Fellows di University of Oxford, UK. Dan beliau adalah Dr. Cica Gustiani. Selamat sore waktu Indonesia, Dr. Cica. Ya,
Selamat sore.
Ya, saya izin pada kesempatan ini memanggil dengan Mbak Cica ya, karena masih muda sekali. Nah, mohon izin saya bacakan sekilas profil dari Mbak Cica. Beliau menempuh pendidikan S1 di Teknik Fisika ITB. Waktu itu bidang fokusnya Computational Material Design ya, Mbak Cica ya. Lulus tahun 2012. Ya. Kemudian lanjut S2 di RWTH Aachen University, bidang Simulation Science. Kemudian setelah itu di tahun 2015 langsung lanjut S3 di kampus yang sama ya, di Aachen University, Germany. Beliau mengambil tema riset terkait dengan protokol kriptografi dan juga terkait dengan implementasi NV-Center qubit ya. Nah, Dr. Cica saat ini berkarir sebagai Postdoctoral Researcher di University of Oxford, dan proyek yang sedang dikerjakan adalah upaya ya mengidentifikasi potensial algoritma yang bagus untuk kita bisa katakan noisy intermediate scale quantum computer gitu. Nah, untuk Kolokium hari ini, Mbak Cica akan membawakan presentasi berjudul Variational Quantum Algorithm ya. Silakan Mbak Cica bisa share screen terlebih dahulu. Sambil menunggu Mbak Cica share screen, sekadar menginformasikan kembali, waktu yang dialokasikan untuk presentasi adalah 1 jam. Setelah presentasi selesai sekitar pukul 17 waktu Indonesia Barat, kita akan membuka sesi tanya jawab. Nah, saat sesi tanya jawab atau menjelang waktu tanya jawab, kami membebaskan Bapak Ibu hadirin semuanya untuk menulis chat pertanyaan melalui fitur Zoom Chat. Silakan juga jika Bapak dan Ibu sekalian ingin bertanya melalui audio dan menampilkan video dengan terlebih dahulu mengangkat tangan atau meminta izin kepada moderator untuk bertanya secara langsung. Mbak Cica, nanti kalau misalnya ada chat-chat pertanyaan yang masuk di tengah presentasi, bisa diabaikan terlebih dahulu ya, karena nanti akan ada Q&A session. Kita akan bacakan di saat sesi tanya jawab tersebut. Nah, silakan Mbak Cica bisa memulai presentasinya dari sekarang.
Ya, makasih Mas Gagus.
Iya, sama-sama.
Jadi kolokiumnya bahasa Inggris ya, soalnya banyak terms-nya lebih mudah di bahasa Inggris, jadi biar flow-nya lebih asik ya, lebih oke gitu. So in this talk, I would like to share about the family of quantum algorithms, so-called variational quantum algorithms, or VQA. So this talk will be a little bit more technical and also kind of dense. So I can expect that you won't understand everything because lacking of details, too much information in the like a short time. So please do not hesitate just to ask questions later in the Q&A session. So in this slide, you see that this is the whole family of variational quantum algorithms that is ranging for various applications. So there are plenty of VQAs out there for different applications, very different techniques, a lot of small tweaks here and there. And the applications can be ranging from the molecular application, for example. So if you can see my cursor here, finding the ground state energy, perform dynamical simulations, also going for the machine learning compilations, combinatorial optimizations, and so forth. So in this talk, I will touch on several applications that includes finding the ground states, and then the dynamical simulations and compilations. They are kind of similar problems, and the combinatorial optimizations, and also some mathematical application, just as an example. So I hope, like in this talk, you will see that all of these algorithms for these different applications, they actually have the very same core. So this just belong to this one variational quantum algorithm framework. And maybe hopefully by seeing this repetitively, you can design your own VQA in the future. Okay. So first, I would like to just to emphasize what does it mean by simulating quantum system on quantum computer. So because the variational quantum eigensolver is one of the algorithms that has the potential to solve practical problems, basically, for example, like finding the ground state energy. So what does it mean by simulating quantum system on quantum computer? First, usually people mean two things. First, the statical and the dynamics property of the quantum system. So in the static property, it means finding the ground state. So you see that this Schrödinger equations, and let's say you want to find the ground state of your Hamiltonian H, and then you see the eigenvalue E. And then the second is simulating the dynamics. So it means simulating the time evolution operator. So if you have the time evolution Schrödinger equation, and let's say your Hamiltonian is a constant, then your solution is just the exponentiation of your Hamiltonian. So like E minus I HT. So this I will address this as either like propagator or the unitary time evolution. So it means that simulating the dynamics on the quantum computer, it means just running this unitary, like the propagator on the quantum computer. Okay. And we will see that all of this can actually be performed in the VQE setting. So in the beginning, solving the static problem, like for example, estimating the ground state, and also actually can be extended to any states, like for example, excited states. The first proposal of algorithm is the quantum phase estimation. So for example, if you have Hamiltonian H, so you have this Schrödinger equation, and then you construct the propagator of a period like tau. And then, so you have the eigenenergy E, and then you can rewrite this E as 2 pi times phi. And then if you have such a form, then you can actually find the phi using the quantum phase estimation. So the quantum phase estimation looks like this. It's a very beautiful algorithm. So I have to remind you that when I say quantum algorithm, I always mean a quantum circuit. So it's just a series of application of quantum gates. So if you see that it's just you can just divide it by tau, then you can have your eigenenergy. So in this quantum phase estimation, your states will be projected into superpositions of the eigenstates of your Hamiltonian. It's a very neat algorithm. So if you here, for example, you prepare first your state. and then you also need all these ancillae on the top. So it's quite depending on how much precision you want to get. And by the end of the algorithm, before the measurement, your state will be in the superposition of the eigenenergy. So this is just binary form of the eigenenergy, and then the last half would be the eigenstate. And so it is so it has this proportion of so it's a superposition of the eigenstates and the eigenenergy, and it depending on how large your coefficient here, then it will be collapsed into the largest coefficient, so with the high probability. So in this case, if you like to find out the ground state, then you have to prepare your state close enough to the ground state compared to the other excited states, so that with high chance your state will be collapsed into the ground state, and also you will just get the readout as the the ground state energy, like on the first. So this is like very neat algorithm, but the problem, the size is growing quite fast. So it grows by precision, basically. So not only precision of the how much precise phi would you like to have, but also the preparation of the U. So U here is like evolution operator. So it's very expensive. You will see in the later some how this U looks like, this propagator. And then on top of that, you have to apply U many times. And you also have to perform the controlled version of this. So imagine that implementing this U actually for most of cases is not exact, so you can only approximate that. So if your approximation is bad, then your final state will be far from the eigenstate of your Hamiltonian. Okay, so it's very expensive. Maybe in the future, when we have fault tolerant, this would be the ideal algorithm. But now, okay, so now we are kind of in the era of NISQ, or noisy intermediate scale quantum computers. So it means we have kind of noisy and from hundreds to 1,000 qubits, and that is not enough for fault tolerant. At the moment, probably we have, actually it's pretty good. It's going pretty fast. We have something like 500, I think, the record. And what we can do on this quantum computer is we try to run some noise resilient algorithms. So this is a type of algorithms that can handle to some degree the noise of the qubits without fault tolerant setting. So another way is adding error mitigation. So it's an extra classical processing. We will see later. Okay. So let's dive into the variational quantum algorithm. So in particular, the finding the ground state. So it's called variational quantum eigensolver, or VQE. So this VQE is inspired from the classical simulator, a so-called Rayleigh-Ritz method. And this has been around since 1950s, I believe. So the idea is you can find the ground state energy by minimizing your Hilbert space. So you calculate the expected value here, and then you keep minimizing the state such that your cost, which is the expected value, will be minimum. So this is a promise that so you can actually just let's say you blindly explore what is the ground state just by trying like this test functions. You try different kind of states, and then you calculate expected value, and it's promised to be always larger than the ground state unless you are in the ground state. Okay, so you can try all kind of the states, but exploring the Hilbert space is extremely expensive. So what people do usually, you construct an ansatz. So you kind of decide a set of bases, and then you just hope the basis can express your ground state. Okay, so you try to and you parameterize a superposition of those bases. So, for example, such superpositions can be expressed with real parameters. So you, in this case, you can just optimize in these real parameters alpha instead of the whole Hilbert space. And then since the optimization is classical, so you can just, and also your energy calculation expected is classical, then if you just find the gradient of the energy or the cost 0, then it means you are in the ground state. Okay, so now the optimization, instead of happening in the Hilbert space, it's a move into the parameter space of this alpha. So it's much a smaller optimization problem. But again, calculating this expected value is very expensive in the classical simulations, because you have a state as the 2 to the power n, so it's exponential, and then you also need to perform this multiplication with the Hamiltonian, so this 2 to the power 2n times 2 to the power n. Okay. So what variational quantum eigensolver, what's the gist is basically throwing this expected value calculation into quantum computer. Okay, you now, because it needs to move into the language of quantum computer, then your ansatz need to be a series of quantum gates. So instead of this superposition of the basis, basically also superposition of the basis, but you kind of encapsulate this into the quantum gates. So you need a series of quantum gates that are parameterized, and then you calculate the cost, which is expected value in the quantum computer, and then the optimization is still performed classically, so you can use any classical optimization method, like simple Newtonian, or I don't know, there are plenty of them out there. So now, instead of storing, because this expected value part is very expensive to simulate and is efficient on quantum computer. Now, instead of having a storage of 2 to the power n, now you only have n qubits to store, right? And this is a lot of saving. So this VQE is basically just this classic Rayleigh's method with the expected value calculated on quantum computer. Okay, so if we just draw the whole VQE framework, so first you have your input. So it is in the problem of the how encode your problem into quantum computer language, and then you calculate the cost, which is normal expected value of your Hamiltonian, and you want your cost to be cheap on quantum computer but expensive on classical computer. So this would be the ideal situation. And then you train your classical parameters and also your ansatz. You can also change them, use some additional algorithms, and then you update it until you reach convergence. So until your cost doesn't change. And then you will have the optimal, free parameters and also the ansatz. So this whole VQE framework can be summarized into the minimizing the these free parameters of your cost, that is expected value. So here is a little bit more details why VQE is attractive to NISQ enthusiasts. So first, it's very flexible. So for example, the ansatz can be designed anything. So if you have quantum, it's depending on your quantum hardware, for example. So for example, here the ansatz is just the product of the quantum gates. And then the second, the Hamiltonian needs to be not to be expressed as a sum of Paulis. We will see how we got into that. Now, since the Hamiltonian is the sum of Pauli strings, then just by linearity, the expected value is also can be done independently in parallel. So for example, this is how it looks like and how to calculate the expected value of a Pauli string. So you can do just Hadamard test. So for example, we have this ansatz on the left side, and then so this is phi theta or phi alpha, and then you add additional ancilla and this Hadamard, and then control of the Pauli, and then Hadamard, and then you perform the sampling, and then the expected value of the outcome will be the expected of the Pauli string, this PJ, for example. Now, since they are like independent to every Pauli terms, then you can just do it independently on different quantum computers, if you like, or like do serially. Now, because of that, instead of like before you saw the quantum phase estimation is very long, now you actually can cut into small chunks on how to run the quantum gate. So in this case, the coherence time requirement is much smaller compared to the quantum phase estimation. That's why this FIKI is pretty good candidate for NISQ computers. And also the optimization is performed classically. So you try to leverage the power of classical computer as well as quantum computer at the same time. And for some noise, it can be actually incorporated into your optimization scheme. So for example, for the noise that are unitary or like static, it usually can be solved by this variational method. Now, the first problem into this scheme is how to express your problem into the quantum computer problem. So for example, in the variational quantum eigensolver, we want to find the ground state energy, right? And you will start with a molecule. So for example, here you start with the electronic configurations Hamiltonian. So the first proposal of the mapping is so-called Jordan-Wigner mapping. It's quite straightforward. So it uses the second quantization. This is because it's quite practical. So your state will be expressed in the occupation number, and then from occupation you can one-to-one mapping into the quantum like qubit states. So if the occupation is 0, it means state 0. If occupation 1 is state 1, so it's quite straightforward. So first, you have to do this you have to convert your Hamiltonian into the second quantization, right? So you just you decide a kind of what basis would you like to consider. So the more basis, of course, the more precision you will obtain, but also it will be more expensive. You will need more qubits. So you choose a basis and then you perform self-consistent field calculation. This one is quite efficient because you only put one electron there. And then after you find the optimal set of bases, then you calculate these the overlap, and then you will have the expressions into the second quantization. And now you have your Hamiltonian in the second quantization. What you have to do next is you convert your operators into the qubit language. So you can, so you basically just need to convert your creation and annihilation operator. So like in the creations, you can just add a projector that looks like this. So it means if your state was 0, and then the output will be 1. So you're creating an extra orbital, something like that. And you just add additional Z here just to track the sign. And then also the same with the annihilation operator. So if you have a state and then you annihilate it to a 0 here. Now, these projectors can simply be expressed as the superposition, or it will be expressed as just additions of Paulis. So it just looks like this. And then now this first part can be expressed as these Paulis, and then the others also like just Z. So in this case, your Hamiltonian is expressed as the sum of Pauli strings. Yeah. So this was pretty straightforward, but I think it's kind of expensive, and there are other mappings out there, so-called Brahikitaev mappings or parity mappings, and if you are interested to have more efficient mappings. And this mappings is also still an open problem, like an active research on how to map your like problem more efficiently, so that you can put as much as information with the small number of qubits. So if we go back to the framework, so we touch on this problem encoding. Okay, now, so we also talk about this calculate the expected value, which is just a string of a Pauli, and you can just do it in parallel fashion. And then now we touch on how to train your free parameters and your ansatz. So first, there are many ways, plenty ways to train your parameters. This is also still an open research problem. So the common one is the steepest gradient descent. So you calculate the gradient, and then you took the directions that is the steepest. So you take the minus, and then you add just some step that you decide. And then this is the new parameter. But for example, another one that in my personal opinion is quite powerful is the imaginary time evolution, or so-called quantum natural gradient. So you see that it's actually very similar, except that you add additional F inverse here. So F inverse is basically the quantum natural gradient, or the inverse of the Fisher information. So by adding this F inverse here, so this is how the quantum Fisher information looks like. You see that for some cases, also in my personal experience, the optimization running way much faster. And of course, there is a little bit more cost to calculate this F. So for example, in this paper that's proposed these imaginary time evolutions, they compare the results of using the steepest gradients. So if you use steepest gradient, so it solves this simple Hamiltonian, is a toy Hamiltonian. And then on the top part is the ones correspond to the low energy, and then the red one correspond to the high energy. And it depends for some cases. So if you start from the high energy, for many cases in the steepest gradient descent, it got stuck into the middle. You see here in the red one. And then the green arrows correspond to the successful optimization, that it will end up in the low energy. So if you see in the top figure, this one using the imaginary time evolution, that even though you start from the high energy, it finds a way to go to the lower energy. So in this is one of the case when everywhere you start, it got successful optimization using the imaginary time evolution. Okay. And now second question is what kind of ansatz, and then the training the ansatz. So there are plenty of, it's also open research problem. The first proposes, of course, fixed ansatz. So you have you decide the ansatz, and then you just change the parameter, and then you hope that it will reach the ground state. And another one is hardware efficient ansatz. So it is depending on the architecture of your hardware. So what capability of your hardware, let's say you can perform only, I don't know, controlled rotations or something like that. And then another one that is powerful, that is probably like the best way, is adaptive ansatz. So you basically adding layer by layers. Like for example, you add a first layer and then you optimize, and then the next you add the second layer and then you optimize, and sometimes you delete some of them. And then many choices of operators. So you have usually you have a pool of operators here. And then in the adaptive ansatz, usually you take the operator from the pool and then you throw to your ansatz, and then you optimize, and then sometimes you keep them, sometimes you delete them, and then there are plenty. So for example, this is adapt FIQE. So this is quite successful FIQE algorithm. And this one is usually useful to implement to solve molecular problems. So many ansatz, I found that the successful ansatz usually tailor to the problems, but sometimes you can also have like agnostic Hamiltonian. So in this case of the adapt, this one is solving the molecular problems. So yeah, Hamiltonian. So for example, so this ansatz is based on the coupled cluster. This is CCSD, coupled cluster single double. So your ansatz in the form of exponentiate something. So it looks like the propagator form. So it's actually kind of expensive ansatz, but you see that for their case, it's quite successful. So for example, this is a case of lithium hydride. And then using the adapt, it's reached pretty good. It's aligned to the exact, and also for the case of beryllium dihydride, and also even for the case of this some hydrogen 6. It doesn't exist, but it's often used as a benchmarking for your algorithm, because H6 is quite a difficult problem. And another example is hardware efficient ansatz. So in this case, for example, you fix because of you have certain layouts. This is an example of the results from the IBM. So for example, in the hydrogen molecule, they are using this Brahms-Kitaev mapping. So you need like less number of qubits. So for example, in this case, they only need 2 qubits for hydrogen molecule. And then they fix this ansatz layout, and then they just varying the parameters with the fixed layout. So for example, you can see that the dashed lines are the exact results, and the dots, the black dots, indicates the running it on the hardware. You see that the energy tend to overestimate, and it's getting worse when you involve more qubits. So involve more qubits also, like you have deeper circuit, that you see that in the beryllium dihydride, it's very noisy, and it's way overestimating than the lowest energy. So what the next stage that you can do is perform error mitigation. So for example, this is so what you do is you have some way to make your circuit worse. So you have, for example, this different dots here. This indicates to some degree 1 time worse, 1.25 times worse, like 2 times worse. And then so you have these samples, so you have way more measurements, and then from this sample you simply perform interpolation. So for example, if you just have 2 samples, and then you have 2 of them, and then you just draw a straight line and then estimate how it looks like without the noise. So this is quite simple, but it's also very expensive. But for some cases, like for the noise, some noise which are not so bad, it performs very well. So you see that if you see this C equal to 1, this is just the, if without anything, then it's overestimating, and then you can just interpolate, and then the final mitigated, error mitigated ones, they are aligned to the the actual energy. And you see that they are actually pretty good in this. And many of them are inside the chemical accuracy. And this is also the case happened for the lithium hydride that they perform. You see that the energy was overestimating, and then you mitigate, and then it's going down closer to the exact energy. Okay, so hopefully you can understand how this VQE, what is the important aspect you need to take care. And now after the static problem, we are going to the dynamic problem. So what does it mean by dynamical simulations? Okay, so we would like to do this dynamical simulation on the quantum computer. So it means first you prepare an initial state, so 0, and then you would like to go to the final state after period time t. So you just apply this propagator, so E minus IHT. And for ideal case, you go straight line, but we don't have the expression to go to the straight way, because we have a limited resource. So we have certain architecture of quantum computer. Okay, so we instead go to some a little bit like a way more like harder way, longer way. So what you do usually, you split the time into you operate into small chunks. So the idea is you try to digitalize, like you try to split into the chunks and something like you watch TV. Basically, you have this actually like analog continuous event, but then your TV is flickering, but it's fast enough such that you don't notice it. So basically, that's kind of the goal that you want to have here. So to do that, so splitting into a small chunks of the unitary such that the error won't be really noticeable. This is can be done using trotterization. This is the standard way. So there are plenty of splitting. So for example, so you have this E exponent A plus B. So A and B is just a set of Pauli strings. So within A, all the Pauli strings are commuting to each other, so it doesn't matter which ordering you want to take. And then also the B commuting to each other, but A and B are not necessarily commute. That's why the ordering is matter here. So the approximation you can do, so this is the trotterization up to the 4th order. In the 1st order, you can just simply cut it into a small chunk, like t minus n. So you have n chunks here, and then you just repeatedly apply these chunks. And then if you do that, your error approximately to be the delta t squared, so t minus n squared. So how does it look like for every Pauli string? So for example, if you have a Pauli string that looks like this, so it's just a single term. And remember that there are many terms in the Hamiltonian. The circuit looks like this. Okay, so it's quite a lot of circuits. And imagine if you have, let's say, so hydrogen has 15 Pauli terms. So this is using Jordan-Wigner mapping. And you have 15 Pauli terms, so you have 15 of this, and then you cut it into chunks, let's say 100, so 15 times 100, so you have 1,500 circuits. Okay. And if you have hydrogen, like a water molecule, you have like 1,500 Pauli terms, so you need to do this like 1,500 times. And so it gets quite expensive pretty quickly. And if you want to get better accuracy, you go to the higher order of trotterization. So it's kind of different way on to cut those chunks, and they actually give you better accuracy. But it's also not that obvious actually. So for example, in the case of the hydrogen, so for example, if you have delta t to 0.55, and then So in this, in the way to read this this curve is the first marker, it means the n equal to 1, so you only have one chunk. And then the second marker is 2 chunks, and then 3 chunks, 4 chunks, and then I think here something like 50 chunks. And then if you just do it like a lot, and you see that it grows the counting, the number of gates is also growing. And then it's not necessarily get better if you just keep doing it in the first order. So for example, if you do it in the fourth order, if you just have 1, 2, 3, 4, 5 chunks, it performed much better than this, than the first order. You get better accuracy. Okay, so this is just how close your unitary approximation of this propagator into the actual unitary. So this is also not really obviously like how does it relate, you know. If, for example, in the third order, you can even get better accuracy than the fourth order, okay, for certain chunks. So this, it's quite expensive. Usually you need like 1,000 of gates to obtain this time evolution operator. Okay, so in the how explicitly looks like, I just want to share you so you have some description. For example, this is the Hamiltonian of hydrogen molecule. So this it has this 15 terms. So we touch on the finding the ground state and dynamical simulation. So if you recall that the dynamical simulation you can do with totalization, but it's very expensive. You need like 1,000 gates, even just for 4 qubits. So in this hydrogen molecule. So like, is there a way to perform it more efficiently? So can you use much less gates than this 4,000, for example? So this dynamical simulating the dynamics can be narrowed down into the compilation problems. So like it's all about how to implement this time evolution unitary operator on the quantum computer. So now we touch on the compilation problem and how to compile using FISIKA. Okay, so just to recall the framework of the variational quantum eigensolver, and you can actually just generalize this into this FISIKA framework. So you encode your problem, now because you want to go into the compilation problem instead of the finding the ground state. You encode your problem into the language quantum computer, and you need to decide what kind of ansatz would you like to have, the kind of initial states, what the parameters, and then you design your cost function and such that in the minimum cost, then you get the true solution. And then you train your parameters, your ansatz, and then you find a way how to train them, and then you just perform the optimization, and then until you find the optimal ansatz and the parameters. Okay, so that's basically just minimizing the cost. Now, the difference between this FISIKA and other, for example, compilation, is mainly designing this cost function that you will see. So, for example, here I would like to compile. So the idea is I would like to synthesize a circuit C that approximates U. So this is the easiest way. So for example, I have an expression of U. For example, it was this very long 1,000 gates of totalization of the propagator, and then I would like to find a shorter version of U. And you can use it for use FISIKA to solve this problem. So if you just throw any random state psi, and then you apply your U, and then this C dagger would be your ansatz, and then your output will be stay the same only if C dagger is U inverse. So if C implements U, then your state would remain. Okay. So what you do, you just instead of preparing a random state, you can just start with a fixed state, state 0, and then you add a random gate, and then you inverse the random gates, and then the final output should be all 0, which is your initial state. It's equivalent. This way, it's actually equivalent to minimizing the expected value of Hamiltonian, that is sum of z. It's the same. And so the cost function will be expected value of your z. So this is the circuit, how the circuit looks like. You prepare in 0, and then you apply random gates, and then your true unitary that is very long, and then you want to find the ansatz, you want to find the optimal solution, and then you undo your random gates, and then this would be expected of the z Hamiltonian. And the cost will be 0, so the minima, so your output all zeros if and only if your C implements U for all kind of test random gates that you throw. And instead of that, you try many random states. You can also do it at once, just once, basically using the maximally entangled state. So this is using Choya-Mikulski state. So this exactly the same, except that you prepare n pairs of Bell pairs, and then you perform Bell measurement, and then if your output all 0 in the end, it means your state, your C implements U. Okay, so you see that if C implements U, this is identity, then the fidelity of phi, so this phi is just the pair of bells, so the bell pairs remains, and then the cost will be 0, will be minimized on the true solution. Okay, so for example, this is how good the result was. So this one is one of the, so this is for over various delta t. If you are using trotterization with error at most 10 to the minus 3 metric distance, you need like, it's growing quite fast, like almost exponentially. For example, this is the highest number on these dots on this various t. If you use trotterization, you need like 1,000 gates. But then if you perform this compilation, try and ask the machine to find the other expression of u, you only need much less and at most 34 gates. So you see that your gates reduce from thousands into 30s, basically. Okay, and for example, in this example, these are the gates that are used, simply just rotation Pauli and then controlled rotations. Okay, now another simple example is linear algebra. So in this problem, you would like to prepare your state into multiplication of some Hermitian M multiplied to your state. So you would like to prepare your state, Vm. Now, so what you can do, you prepare a Hamiltonian that is that looks like this. That is basically a projector. So there is an efficient way to do that. And then your cost is simply just the expected value of your answer state. So if you design the cost like that, then you just go through. If your ansatz implements this goal VM, then it will have fidelity once. It will have overlap once. Then your cost will be 0. So if and only if phi, your ansatz actually implements your solution. Okay, and wow, it's going pretty fast. So last but not least, so this. The last variations of the VQA is like QA or A. So this is kind of a little bit different with the VQE. and the quantum optimization algorithms. So in this case, you kind of change the Hamiltonian adiabatically. It's quite different. So for example, this QAOA can solve a max-cut problem. So in max-cut problem, basically, you want to partition a graph into two parts such that the edges between two different graphs are maximum. So for example, if we have this graph, and then I partition into two graphs, and then the graphs are encoded as purple and yellow. So if I partition this way, the edges is maximum, for example. So it's the edge between two different graphs. So I would like the number of edge between two different colors to be maximum. So in this case would be like 1, it's like 2, 3, 4, 5, 6. So we have 6 edges, and this solution can be described by the binary. So if I have 1, if I have 1, it means the purple graph. If I have 0, it means the yellow graph. So this would be the solution. Now, this problem is an NP-hard problem, and it has been performed iteratively, also using the binary optimization, using classical computer. Okay, so for example, if we design the cost like this, so if we have, so ij is going through edges. So if the edge I correspond to the vertex purple, then I will put 1. If j is, let's say, correspond to yellow, then this would be 0. So this would be 1 times 1. So it will be 1. And if they are on the same, let's say 4 and 6, so they're both 1. So this will be 1 times 0. So it will be 0. So the maximum cost will be the solution. Okay, so that's maximizing. But if you just add minus in the cost, then it will be minimization problem. So it's just the same thing. So now the goal is how to translate this into QAOA, is finding the cost Hamiltonian such that your cost and you can correspond your eigen the ground state will be the cost, the minimum of the cost, or like minus maximum is the same thing. Okay, now this classical, in the classical setting, it's called QUBO, so quadratic unconstrained binary optimization problem. So basically the goal is how to describe this QUBO into the quantum computer. So there is a way to do that, and I'm not going to go into details, but there is a recipe for that already, even for if you put weights into your edges. So the goal is to find the cost that is even including weight. So you multiply by the weight, the maximum total. And to do that, so you just map. So you first obtain your cost Hamiltonian, this HC, and you see that it actually just a lot of Z terms. Okay. And then from here, you another things you need is a mixer Hamiltonian. So for example, this is the commonly used mixer Hamiltonian, that is just sum of x. So the idea of this QA is you start from the mixer. So because you know what is the ground state of this Hamiltonian is basically just product of plus states, right? And then you evolve using the same idea as trotterization before, that you saw before. You start with the mixer, and then also if you at time t equal to 0, you have this completely mixer Hamiltonian, and then you start at the ground state of your mixer Hamiltonian, and then over the time after capital T, you see that this becomes 0, and then you will be in the cost Hamiltonian, which is your Kubo problem. Now, the idea you have this repetitions of the mixer. So this E minus I HM, and this is the free parameters that you optimize, and then you perform the cost Hamiltonian. So this is the same as small evolutions of the trotterization idea. You start with the idea, if with this adiabatic evolution, if you start at the ground state of a certain Hamiltonian, which is the mixer, so you start with this ground state of the mixer Hamiltonian, after a certain of time, you will stay, if you move slow enough, so the evolution described by this alternating alternating of the
Dr.
mixer
Cica,
and
sorry,
yeah,
just to remind that you have 5 minutes left
yes, it's
to
the
wrap
last
up
slide,
your talk.
don't worry.
Okay.
Yeah, so the idea, if you stay in the ground state of mixer Hamiltonian, your final state will be the ground state of your cost Hamiltonian. So you kind of just change your landscape slowly. Okay. Now, so you first optimize with your parameterize the propagator, and then after you have the optimized gamma and beta, then your solution will be the maximum distribution of your state. So let's say if the maximum the maximum probability of states 3, then the 3 would be your solution, basically. Yeah, and yeah, that's basically was the last slide. So I'm happy to take any questions.
Okay, thank you to our presenter for sharing your insight with us. Very, very interesting talks, and we do really appreciate Dr. Cica for your time and also effort you put into preparing the presentations. And today's discussion is regarding the variational quantum algorithm. Specifically, Dr. Cica has already explained regarding the ADAPT VGA algorithms and how to improve the error mitigation in this algorithm. And last but not least, Dr. Cica also introduced about the KUAA to solve math problems. So in summary, variational quantum algorithms is used in quantum computer to solve the optimization problems by iteratively adjusting the parameter of a quantum circuit to minimize the cost functions. However, in quantum computer, there are a lot of error due to noise or decoherence, so we can affect the accuracy of the algorithm. So error mitigation technique is important to improve the accuracy of the algorithm. So now I would like to open the floor to questions from our audience. Please feel free to ask any question you might have. Baik, ini dalam bahasa Indonesianya. Terima kasih ya Dr. Cica. Materi dan sharingnya dari Dr. Cica sangat menarik dan menambah wawasan kita tentang quantum algorithm ya. Jadi para pendengar kami persilahkan untuk menyampaikan pertanyaannya melalui fasilitas chat di Zoom, atau silakan jika ingin bertanya secara langsung dengan terlebih dahulu meminta izin melalui fitur raise hand. Nah, pada sesi tanya jawab ini bisa bertanya langsung ke Mbak Cica atau melalui fitur chat dengan bahasa Indonesia ya, nggak apa-apa ya Mbak Cica? Untuk mengakomodasi semuanya. Jika ingin berdiskusi lebih supaya bisa lebih memahami apa itu quantum algorithm, quantum circuit, quantum gate dan lain sebagainya gitu.
Bebas. Agak di luar juga nggak apa-apa kalau masih konteks quantum information.
Iya, ya. Terima kasih banyak nih Mbak Cica. Jadi kalau dari chat ini, ini dari Pak Ahmad Ridwan ya. Can we do VGA in our laptop? Jadi mengerjakan quantum algorithm dengan menggunakan classical computer nih, Mbak Cica, bagaimana?
Sangat bisa. Jadi biasanya kalau misalkan tadi kan ada there are different aspects that we have to take care. kayak misalnya pilih ansatz yang gimana atau gimana cara train parameternya. Jadi ada banyak cara gitu. Jadi biasanya benchmarking algoritmanya bagus atau enggak itu disimulasikan di komputer biasa, di laptop biasa. Jadi kalau misalnya jadi saya juga kayak tes algoritma di laptop. Jadi kalau misalnya di laptop itu jadi di kalkulasi expected value-nya, artinya jadi gimana ya? Kalau misalkan dilihat di let's go back to this. Oke. Artinya di bagian sini itu bukan di quantum computer tapi di laptop gitu ya. Jadi Anda harus tetap so you still have to put the states, simulate the states into factor of this complex factor to the power n, and then you have to perform matrix factor multiplications. So you still have to do this full classical simulations that is growing exponentially. Now, kayak menjawab nggak?
Mas Ridwan, apakah ada pertanyaan lebih lanjut? Jadi basically bisa ya, Cica. Jadi
bisa.
Jadi it also can be conducted in Google Colab, I think, yes, by using simulators.
Yeah. Jadi dibatasi berapa giga memorinya gitu. Jadi kalau misalnya kalau misalnya punya 16 giga memori gitu biasanya bisa berapa ya? Sekitar 12 qubits bisa. 12 agak lama gitu, 16.
Iya. Dan mungkin perlu ini ya, cutting gradiennya ya. Gradient sirkuitnya yang bisa menghasilkan nilai 0 kali ya. Jadi nggak semua qubit dipakai.
Gimana maksudnya?
Jadi adap algoritmnya tadi mungkin. Jadi nggak perlu menyederhanakan sirkuit kalau misalnya quantum bitnya terlalu banyak kalau di classical computer.
Kalau misalnya quantum circuitnya banyak, artinya kan lama.
Jadi
lama.
kayaknya
Tapi memang ya lama aja, tapi nggak ada error kan, jadi nggak dibatasi sama coherence time.
Okay.
Ya.
Apakah menjawab Mas Ridwan atau mungkin perlu bertanya lebih lagi melalui ini audio atau video? Mungkin cukup ya. Jadi di pertanyaan kedua Mbak Cica di chat ya dari Pak Mohon Sidik, how about the barren plateau in optimization?
Nah, jadi barren plateau itu masalah yang besar di VQI. Jadi di barren plateau itu bisa dibatasi, yang membuat barren plateau itu ada expressibility. Jadi kalau misalkan ansatsnya itu kurang ekspresif, udah nggak bisa, udah mentok gitu, udah nggak bisa mengekspresikan state yang dekat dengan ground state. Nah itu salah satu barren plateau. Yang kedua itu barren plateau dari noise. Barren plateau dari noise itu jauh lebih severe gitu ya, jauh lebih parah. Jadi kalau kalau misalnya kuantum, jadi cost-nya itu kan expected value ya, expected value. Terus kalau misalkan expected value-nya itu, kalau misalkan quantum state-nya itu dikasih misalnya depolarization. Jadi qubit-nya itu, state-nya itu pergi ke tengah gitu ya. Jadi kayak it's restricted to like a small space. Jadi udah nggak bisa, kalau misalnya single qubitnya itu kan harusnya blow sphere gitu ya. Jadi bisa ekspresikan kemana aja. Jadi kalau misalnya dapat depolarization noise jadi ke tengah gitu, jadi complete mix, jadi nggak bisa ekspresikan yang di luar itu. Jadi karena kalau misalkan terlalu noisy, si qubitsnya itu udah nggak bisa mengekspresikan state yang di luar tadi. Jadi barren plateau itu biasanya dari noise yang jauh lebih parah atau dari desain si ansatsnya. So, jadi lebih ke permasalahan expressibility.
Kalau kayak gitu ada strategi nggak, walaupun ansats nggak mutlak ya untuk sistem tertentu gitu, maksudnya bagaimana ya cara kita untuk mendapatkan ansats yang bagus gitu. Jadi
Jadi kan tadi ada banyak cara, misalkan adaptif gitu. Jadi kasih ansats cuman satu layer, terus kalau misalkan terlalu ekspresif ya, kalau misalnya terlalu banyak quantum gates, jadi si parameternya ada 1000 misalkan buat hydrogen, itu terlalu si gradiennya itu jadi rata gitu, jadi datar. Jadi kalau misalkan terlalu banyak axis di parameter, jadi kalau misalnya cuman sedikit ke sana, itu udah rata gitu. Jadi over parameterization, terlalu banyak parameter, itu bikin bisa induce barren plateau. Jadi biasanya adaptif, jadi satu layer, udah gitu dioptimisasi, udah gitu tambah layer lagi, optimisasi lagi. Terus kalau misalkan ada kira-kira gates yang nggak guna gitu, di delete gitu. Jadi biar parameternya lebih sedikit. Juga kalau misalkan ada noise kan, kalau misalnya gatesnya lebih sedikit, noise-nya lebih sedikit. Jadi it's still an open problem. Dan lebih ke expressibility.
ya, Mas Madis, cukup atau
Ya, cukup.
cukup? Ya. Untuk pertanyaan selanjutnya dari ini ya, dari riset yang di Pusat Riset Fisika Kuantum ya, Brin. How does KUA compare to other optimization algorithm? Jadi bagaimana algoritmanya KUA ya kalau dibanding dengan algoritma optimisasi yang lain? Tergantung aplikasi ya, sepertinya Mbak Cica ya.
Tergantung aplikasi, ya. Tergantung aplikasi. Ya, kurang tahu juga.
Ya, mungkin ini ya tergantung.
Terus QAOA juga kan masih open research gitu. Jadi kita tuh nggak tahu kalau misalkan benar-benar ada advantage dari quantum computer gitu atau enggak. Mungkin classical lebih cepat.
Ya. Jadi itu untuk pertanyaan selanjutnya dari Mas Roni Muslim, ini juga periset dari Pusat Fisika Kuantum Brin. So far, is there a good method to determine the guess, stat, or unstat to get the good result? Apakah ada ini ya, tadi ya yang sudah dibicarakan, jadi bagaimana cara metode yang paling bagus untuk memperkirakan ansats untuk menghasilkan ground state yang benar-benar mendekati ground state gitu.
Jadi biasanya kalau yang mudahnya itu kan tailored to problems. Jadi kalau molecular problems biasanya pakai tadi UCCSD couple cluster ansat yang ada VQ itu kayak cukup bagus gitu. Terus kalau misalnya spin chain problem, jadi kira-kira ansatnya nearest neighbor gitu-gitu. Biasanya seperti itu. Terus itu kan kayak kira-kira how to determine the gate pool. Jadi gate poolnya kayak apa biasanya dikonstruksi tergantung masalahnya. Terus pakai adaptif tadi. Jadi selama optimisasi si ansatnya itu terus di-update gitu.
Ya. Kalau selain USCC itu ada lagi nggak ya framework lain yang bisa dipilih? Saya pernah nyoba sih Mbak Cica pakai itu ya, tapi karena qubit yang saya pakai sedikit, jadi itu too much kalau pakai framework itu gitu. Jadi ada yang menghasilkan gradiennya 0, sehingga kita harus menghilangkan beberapa gradien yang menghasilkan 0, dan itu banyak banget gitu. Walaupun kita cuma pakai berapa qubit ya, 12 qubit tuh yang gradiennya nggak terpakai, ternyata banyak dari USCC ansas gitu.
Metode lain, kalau 12 qubit itu molekul apa?
Nggak bisa, misalnya sih itu tadi.
Ya,
Jadi
ada banyak sih, banyak kok. Misalnya kalau saya juga pernah cuman pakai kayak rotation sama conditional rotations, dan itu cukup gitu. Dan juga lebih sedikit. Jadi kayak sebenarnya ansat apa aja bisa.
jadi
Jadi
nggak
kira-kira
harus tinggal double excitation gate ya?
enggak. Jadi
Nggak harus.
selama poolnya itu cukup buat universal computation, bisa.
Oke, kita lanjut pertanyaan kedua dari Mas Roni ya. Suppose we combine PKA with the concept of neural network, where each layer contains a complete set of unitary operators, including nonlinear function. Theoretically, we will obtain a better result by increasing the number of layers. However, we have an experience that adding an n double layer does not yield better result, instead violating the PKA concept. According to you, what's wrong with that? Jadi terkait penambahan layer ya.
That's ya mungkin. So I'm not. Saya nggak familiar sama neural networks juga.
Oke, kita lanjut ya.
Mungkin
Atau ada
Mas Gabus punya
belum sih,
jawaban.
saya juga masih basic belajarnya. Kalau yang ke neural networknya belum.
Yeah, sorry, I don't have an answer for that.
Dari ini ya, dari Mas Reski, ini juga peneliti riset dari Pusat Riset Sosial Kuantum sekarang lagi postdoc di Luxembourg ya. Terima kasih atas presentasinya, sangat advance sekali. Kalau mau mulai belajar menggunakan komputer kuantum untuk permasalahan fisika yang paling sederhana, Hamiltonian apakah atau permasalahan apakah yang bagus untuk belajar? Adakah paper pedagogis yang dapat dijadikan referensi untuk belajar?
Untuk VQI atau komputer quantum information in general?
Untuk permasalahan fisika yang paling sederhana.
Permasalahan fisika paling sederhana itu biasanya Ising spin model biasanya. Jadi spin interaction nearest neighbor Hamiltonian. Biasanya.
Apakah Mas Reski ingin bertanya secara langsung atau sudah cukup? Oke. Kalau misalnya ini ada beberapa pertanyaan, soalnya kita lanjut lagi ya. Jadi ini pertanyaan dari Mas Yusrul. What are some challenges in implementing KUA and what is the future of KUA? Jadi challenge menggunakan KUA sama menurut Mbak Cica ini prediksi ke depannya QAA untuk misalnya dikasihkan contoh untuk aplikasi tertentu bagaimana, apakah bisa solve the problem atau jangan-jangan malah klasik komputer bisa lebih bagus gitu.
So QAO itu permasalahan yang the least familiar. Jadi saya yang paling nggak ahli di QA. Jadi kalau misalnya cuma saya lihat dari algoritmanya itu jadi preparation is a problem. Jadi kan tadi kan ada mixer Hamiltonian, terus prepare di ground state dari si mixer Hamiltonian. Terus kan ya apa sih garansi dari si mixer Hamiltonian ini bisa ke cos Hamiltonian. Jadi ada permasalahan gimana caranya pakai mixer Hamiltonian yang gimana gitu. Kayaknya di situ sih. Soalnya kalau misalnya dilihat dari, kalau tadi kan kalau misalnya di contoh mixer Hamiltonian tadi, I can join the page. Nggak bisa dong. Jadi kalau misalnya di mixer Hamiltonian tadi, kalau misalnya cuman X, sum of X, itu the propagatornya itu kan simple, cuman Rx rotation. Jadi kalau misalnya dari sisi implementasi gates, kayaknya cukup simple, sama si cos Hamiltoniannya juga kayaknya cukup simple, soalnya cuman kayak z terms. Jadi bentuknya kayak Control Z, RZ, kayak something like this, quite simple. Tapi juga nggak tahu gitu seberapa banyak repetitions diperlukan. Kayaknya permasalahannya di situ. Cuman saya belum pernah secara langsung kayak play around with QA gitu.
Ya. Terima kasih Mbak Cica. Yang penting kita udah dapat hint-nya ya, keywordnya adalah mixer Hamiltoniannya ya untuk VQA problem.
Iya, misalnya.
Jadi untuk pertanyaan selanjutnya, karena ini lumayan banyak pertanyaan, jadi pertanyaan dari ini Pak Khairul Anwar, ini dari Telkom University ya. What is the most important thing we should take care of when we use or design a VQA?
Okay. What's the most important thing?
Apa yang perlu carefully kita consider?
The cost function is very important. Nah, ya, jadi kan tadi permasalahannya designing the cost function. Kalau cost functionnya beda, landscape optimization-nya juga beda. Gitu.
Berarti
jadi kadang-kadang ya, yang ngasih path-nya beda.
Untuk pertanyaan selanjutnya dari ini Pak Ajis ya, dari Universitas Indonesia. When you try to solve a quantum problem like electronic state in a molecule using quantum algorithm on a quantum computer, how do you construct the quantum state out of your qubit? How many qubit do you need?
Jadi kan tadi permasalahannya itu mappings-nya kan. Jadi kalau misalnya iya, Jordan Whitner contohnya. Ada juga Brafikitaev. Jadi ke second quantization, dari situ terus mapping tadi Jordan Whitner. Nah, jadi kalau misalnya tadi permasalahannya tadi kan kalau misalnya pakai VQE, jadi tadi variational. Terus yang kedua pakai quantum phase estimation juga bisa gitu.
Okay.
Jadi kalau pakai quantum phase estimation ada tambahan ancilla. Jadi tergantung mau akurasinya mau segimana gitu. Kalau tambah qubit tambah akurat. Jadi kayak tadi kalau misalnya tadi kan dari second quantization itu kan si basisnya itu Slater determinant. Nah, dari Slater determinant ini kan ada orbital, jadi ditentuin dulu gitu ada orbitalnya yang mau dipakai apa aja. Jadi kalau standarnya ini yang biasanya sering digunakan itu cuman kayak s orbital aja gitu. Jadi nggak akurat. Jadi itu juga permasalahan. Jadi kalau misalnya mau tambah orbital, tambah akurat, tapi kan qubitnya tambah banyak. Gitu. Jadi tergantung. Jadi kalau misalnya sangat akurat, qubitnya tambah, tapi kalau nggak akurat, lebih sedikit qubitnya gitu. Jadi lebih sedikit orbital.
Oke, itu ini ya Mbak Cica, term of active orbital kali ya. Jadi
ya,
nggak semua orbital dipakai karena memang computation time-nya akan semakin banyak. Jadi active orbital biasanya ya kalau di DFT electron valence gitu ya, mungkin yang dipakai gitu. Pertanyaan selanjutnya dari Intan, if we use cloud server more faster like Google Pro or Colab, which are better of both of the cloud? Please review perform of both because we are stressed while we are training a large data. Oh, ini tentang penggunaan cloud server. Jadi kalau misalnya running pakai simulator mungkin ya. Jadi kalau misalnya di Google Pro atau Colab ini gimana untuk kecepatannya gitu. Kalau misalnya kita dealing with training large data. Jadi diasumsikan qubitnya banyak sekali ini pasti ya. Apakah itu possible pakai simulator dan kita run di Google Colab gitu? Atau mungkin kita harus memang akses quantum hardware-nya gitu?
Saya belum pernah pakai Google Colabs. Nggak tahu,
Hmm.
mungkin Kak Gus punya pengalaman. I don't
Ah,
have an experience
ya
of
itu
that.
kalau kalau saya nyoba tapi belum tentu benar juga ya. Beberapa itu tergantung device. Jadi kan simulator biasanya kita punya device tersebut itu library dari misalnya kalau Pennyland itu ada beberapa yang device yang kita gunakan sebagai default atau kita bisa pakai device dari Qiskit gitu. Nah kalau kita bisa misalnya
Hmm.
pakai device-nya dari Qiskit itu akan lebih lama kalau kita pakai Google Colab. Tapi kalau pakai automatically atau default-nya dari simulator tersebut akan cepat sih gitu. Tapi lagi-lagi tergantung jumlah qubit yang dipakai gitu.
Hmm.
Sama ini cutting sirkuitnya ya, yang gradien yang menghasilkan nol itu kita bisa cut gitu. Kalau itu dari pengalaman saya sih Mbak Cica.
Jadi kalau misalnya pakai simulator kan,
Uh,
calculate expected value-nya itu lebih cepat kan?
lebih
Soalnya,
cepat classically.
kalau misalkan kalau pakai quantum computer kan harus kayak shots gitu, many
Hmm,
shots.
hmm,
Terus juga for each terms, misalnya 1000 shots. Jadi misalnya ada 1500 terms, berarti 1500 dikalikan
yeah.
1000 shots. Jadi kan jadi lama banget kalau misalnya pakai
Hmm.
komputer quantum.
Shotnya ini measurement ya rekan-rekan semua. Jadi
Ya,
kalau
measurement.
kalau measurementnya terlalu banyak, jadi almost impossible if we use simulators. Jadi Kak ada iteratif. Jadi memang ini sih kita harus pinter recognize pertama kali jumlah qubitnya berapa, sistem kita seperti apa, sirkuitnya seperti apa, dan yang terakhir adalah shot yang kita pakai itu berapa gitu.
Ya, jadi kalau misalkan pakai simulator lebih cepat kalau dikalikan gitu, nggak pakai shots.
Iya, iya.
Jadi kayak back to the classical simulation.
Pertanyaan selanjutnya Mbak Cica ya, ini dari Mas Taruli Jarenia Halasan Sinaga dari Telkom University. How to know if PKA or KUA has reached ground state?
Biasanya si gradientnya 0. Jadi kalau misalnya gradiennya udah rata, tadi kan di theta equal to 0, kayak optimisasi biasa gitu, itu udah kayak minima. Tapi kan kita nggak tahu itu local minima atau global minima gitu, jadi tetap the same problem.
Iya.
Jadi si finding the ground state itu kompleksitasnya kayak Merlin Arthur gitu, QMA. Jadi kita punya solusi dan kita nggak tahu gitu ini apakah benar solusinya atau solusi lokal. Gitu. It's this hard problem.
Ya. Oke. Pertanyaan selanjutnya dari Mas Jauhar Kolili dari Pusat Riset Fisika Kuantum, BRIN. Apakah pernah mengalami masalah seperti berikut ketika meminimalkan energi menggunakan variational principle, energi sesuai referensi ketika iterasi kecil, tapi energi selalu turun di bawah energi ground state setelah angka iterasi yang besar. Kalau tidak pernah, mohon komentar tentang problem seperti ini.
Belum pernah. Jadi kalau misalnya iterasi terus si cost-nya itu di bawah ground state, itu artinya kayaknya bugs. Jadi kan tadi si variational principle really reads variational principle. Jadi itu promise gitu. Itu udah promise that for every states will be larger than the expected value will be larger than the ground state unless it's in the ground state. Jadi kalau misalnya di bawah ground state itu berarti mungkin Hamiltoniannya salah, atau kalau misalkan pakai error mitigation itu kadang-kadang tadi kan interpolasinya itu kayak undershoot gitu, jadi kayak terlalu salah gitu. Kadang-kadang kalau di error mitigation happens, tapi kalau nggak pakai error mitigation biasanya Hamiltoniannya salah gitu. Soalnya kalau misalkan pakai noise itu nggak akan di bawah ground state, tapi overestimate. It's always overestimating.
Oke. Jadi ini sebenarnya ada juga yang raise hand ya, tapi ini saya selesaikan dulu yang di chat ya, karena waktunya juga teman-teman di Indonesia mungkin juga persiapan buka puasa, tapi ini masih banyak pertanyaan.
Saya ngabuburit.
Ini
Ya.
Bu Cica di bawah David Di Vincenzo waktu di Jerman ya. Kalau di Oxford sekarang di bawah
Oh ya.
siapa? Kalau di Oxford siapa?
Simon Benjamin.
Tuh, itu ya Mas Muhandis. Kemudian dari Pak Ayes lagi.
Masih muda ya, profesornya ya, dibandingkan David. Dibandingkan
Apakah masih muda?
Vincenzo.
Lebih
Masih
muda nggak?
ya, profesornya. Dibandingkan di Vincenzo.
Lebih?
Masih muda dibandingkan
muda,
di Vincenzo.
Oh, nggak. Lebih muda tapi nggak begitu muda gitu. Dia cuma kelihatan muda aja.
Oke, kita
Soalnya
lanjut pertanyaan.
siswanya dia udah ada yang jadi profesor gitu.
Ini ada pertanyaan lagi dari Pak Ajis ya, apakah semua quantum problem solving dengan menggunakan quantum algorithm yang dijelaskan tadi betul-betul telah direalisasikan di quantum komputer atau baru sebatas simulasi di classical komputer? Berarti di sini kubitnya
sudah.
Ya. Okay.
Sudah direalisasikan di komputer kuantum. Ya. Tapi nggak sebatas yang apa ya? Kalau misalnya molekulnya besar gitu, kalau misalnya kayak targetnya itu misalnya kalau molekulnya terlalu besar kan nggak bisa di classical. Tapi kalau misalnya ada batasannya gitu. Jadi yang pernah dicoba itu cuma molekul yang kecil, jadi masih bisa diselesaikan di classical komputer gitu. Jadi belum begitu apa ya, advantage-nya itu belum diambil gitu karena size.
Makanya ini ya Mbak Cica disebutnya adalah near term quantum computer. Gitu. Jadi mungkin bisa di quantum hardware yang sebenarnya gitu, tapi memang case yang kubitnya masih sedikit gitu untuk molekul-molekul. Gitu.
Sedikit. Iya. Kalau kubitnya terlalu besar, terlalu banyak noise, bareng Plato.
Nah ini terus ini jika ada pertanyaan yang langsung kepengen ini ya, bertanya secara langsung bisa raise hand. Saya mulai dari Mas Fikri Abdillah ya.
Suara saya sudah terdengar?
Iya, sudah terdengar.
Ya.
Terima kasih. Di sini saya ada 3 pertanyaan. Pertama masalah encoding ini, apakah ada cara gitu mengencode data biasa ke qubit? Pertama.
Cara mengencode?
Encode data biasa ke qubit.
Mungkin registernya Mbak Cica.
Cara mengencode register?
Dari quantum stage, dari quantum
dari classical stage dulu, dari classical stage ke quantum stage. Cara mengencode data.
Ya tadi. Jadi sama aja kayak classical gitu. Jadi kan ada kalau misalnya di framework FIQ ini biasanya orang pakai second quantization. Jadi tadi encodingnya pakai second quantization. Jadi punya state-nya occupation number kan. Nah ada juga yang di first quantization. Jadi kayak standar kayak XYZ gitu. Jadi di first quantization kan koordinat. Jadi koordinat kan kalau misalnya disimulasikan di classical komputer klasik biasa juga pakai bilangan biner kan sama aja. Nah dari bilangan biner di convert ke quantum state juga bisa gitu, tapi lebih ekspensif.
Oke. Terus yang kedua, ini kita sebelum kita merangkai ansatz, kita tuh ngitung dulu nggak apa namanya itu unitary gate-nya kan Ustaz? U-nya gitu.
Ngitung apanya?
U-nya.
Ya.
U itu kayak unitary gate gitu.
Kayak misalnya di compilation
gitu.
problem.
Kayak gitu.
Ya.
Sebelum kita merangkai, ini kan U-nya ini kan kumpulan rangkaian kan?
Unitary.
Dalam U ini, sebelum kita merangkai, kita ngitung dulu.
Jadi tergantung gitu. Kalau misalkan, jadi kalau di sini kan semuanya di komputer kuantum gitu, ideally. Jadi kayak misalnya kayak U-nya itu kalau U trotterization kayak U-nya seperti ini gitu. Jadi sangat panjang, jadi kayak seperti ini. Terus banyak termnya sampai ribuan. Nah, jadi tahu gitu, U-nya tahu cara konstruksinya. Terus kita tuh pengen cari alternatif sirkuit yang jauh lebih shallow gitu, jauh lebih sedikit.
Berarti di sini kita ngitung dulu. Apa Mbak lanjutin Mbak?
Bisa di ini dulu di tahu cara aplikasi U-nya dulu, tahu dulu.
tahu aplikasinya punya dulu baru ngitung.
Ya, baru optimisasi ya. Jadi kadang-kadang kalau misalnya di simulasi lebih mudah ya, kalau misalnya U-nya itu apa aja gitu, random unitary. Terus gimana cara aplikasi pakai quantum gates juga bisa. Tapi kalau misalkan simulasi.
Oke.
Waktunya sudah habis ya. Jadi tadi tinggal satu pertanyaan lagi ya. Jadi habis ini selesai ya.
Iya.
Fikri silakan kalau misalnya masih ada satu kali pertanyaan lagi. Ini juga udah 17.30 nanti khawatirnya
Udah azan.
di Indonesia.
Ini boleh saya tanya lagi gitu. Pertanyaan
Satu
terakhir.
kali lagi habis itu selesai ya.
Oh ya, satu kali lagi. Ini untuk semuanya, bukannya untuk Cica. Jadi saya pakai analogi aja. Jadi saya sudah 4 tahun lulus dari saya dapat gelar sarjana 2 tahun lalu. Terus saya punya ide saya mau publikasi. Nah, tapi saya saya pengen cari supervisor, terus juga dana sama alat-alatnya gitu. Alat yang dibutuhkan untuk eksperimen. Nah, misal saya ngajuin itu ke Mbak Cica gitu, dengan harapan saya dapat supervisornya Mbak Cica, sekaligus ilmunya dari Mbak juga, terus juga dana untuk publikasi ataupun untuk eksperimennya juga, sama alat-alatnya. Apakah Mbak mau gitu misalnya gitu? Misal aja.
Itu ya. Kalau itu susah ya, soalnya saya nggak punya grant sendiri gitu. Jadi soalnya saya juga pakai grantnya si profesor. Jadi kalau lebih mudah itu cari yang levelnya tinggi gitu, level profesor. Jadi biasanya profesor punya dana sendiri.
Oke. Karena saya sebenarnya belum berniat untuk masuk master dulu, jadi tapi pengen publikasi juga.
Mungkin bisa
Mungkin
koordinasi
ada jawaban lain.
dengan Brin.
Mungkin nanti Mbak Cica bisa suggest potensial supervisornya yang memungkinkan, atau kita doakan saja Mbak Cicanya bisa segera ini ya, setelah postdoc punya independent position yang punya agresivitas merekrut rekan-rekan dari Indonesia yang ingin belajar quantum computing gitu ya.
Amin.
Oke, terima kasih Mbak.
Ya, karena waktunya sudah
makasih.
habis ya ini ya. Tampaknya seru sekali nih teman-teman, masih banyak bertanya nih Mbak Cica, tapi karena waktunya telah habis. Jadi Kolokium pada kesempatan kali ini kita akhiri segera. Kami ucapkan terima kasih sebesar-besarnya kepada Dr. Cica yang telah meluangkan waktunya berbagi ilmu di tengah kesibukan yang sangat sibuk sekali nih. Saya dengar lagi di Jerman nih ya. Jadi posisinya waktu kita make appointment-nya lagi di UK, tapi sekarang udah lagi di Jerman, jadi tadi menyesuaikan waktunya gitu. Dan saya ucapkan juga terima kasih kepada panitia Kolokium dan juga rekan-rekan semua yang hadir pada Kolokium Fisika Kuantum, Badan Riset dan Inovasi Nasional. Kolokium Fisika Kuantum BRIN tentunya tidak akan bisa terlaksana tanpa partisipasi aktif Bapak Ibu sekalian. Ikuti terus Kolokium Fisika Kuantum BRIN. Nantikan informasi detailnya sekitar, biasanya kita post beberapa hari sebelum pelaksanaan Kolokium. Kita post di laman Facebook dan Instagram Pusat Riset Fisika Kuantum BRIN dengan nama akunnya, jangan lupa ya, quantumresearch.id. Sampai jumpa di Kolokium berikutnya. Tetap semangat, selamat, bersiap berbuka puasa bagi teman-teman yang menjalankan ibadah puasa. Demikian kami akan end meeting for all saat ini. Wassalamualaikum warahmatullahi wabarakatuh.
Wassalam.